Electron configurations is a topic in chemistry that can be confusing to some people, but with the right information, this concept is actually pretty easy to understand. In this video, I'm going to be talking about what electron configurations are and how to write them using a periodic table. If you're new to this topic or you simply have questions, this video is perfect for you. I'm going to try to explain everything thoroughly, so hopefully by the end, all your questions will be answered. Let's get started. In order to start writing electron configurations, we first have to learn what they are. The internet definition for this is, the electron configuration is the distribution of electrons of an atom or molecule in atomic or molecular orbitals. So right off the bat, this definition can seem confusing. So let's break this up. Let's focus on this word orbitals. This is important. When we look up a picture of an atom, whether it's on internet or your textbook or anywhere, we see this generic picture. And when we think of atom, this is what we think of. And you can see the electrons surrounding the nucleus, and they're going in this oval-like orbit pattern. But in reality, atoms aren't as neat as this. They're way more complex. So if this isn't what an atom looks like, then how does it look like? How can we tell where the electrons are in the orbits? How can we tell what the orbits look like? This is why orbitals and understanding them is important. The definition of an orbital is regions of space around the nucleus of an atom where an electron is likely to be found. So here's a picture of what we're talking about. And right off the bat, this seems like a complex picture. But let's take a look. Over here we have 4 subshells. We have the S subshell, the P subshell, the D subshell, and the F subshell. Each subshell is made out of one or more orbitals. So for example, S has 1 orbital, P has 3 orbitals, D has 1, 2, 3, 4, 5 orbitals, F has 1, 2, 3, 4, 5, 6, 7 orbitals. The bubbles that you see in each diagram, that's the likeliness of where each electron is present. So essentially, orbitals are the percentage of likeliness where electrons are present. Each orbital, so each diagram, holds 2 electrons. So S only has 1 orbital. So that means in the S subshell, there's only 2 electrons. P has 3 orbitals. So the P subshell can hold 6 electrons. D has 5 orbitals. So it can hold 10 electrons. The F subshell has 14 electrons because it has 7 orbitals. So you might be asking yourself, what are these subshells and what do they mean? Well, each subshell represents a different energy level, with S being the lowest and F being the greatest. Just remember the order S, P, D, F. As you go down the periodic table, the atomic number is going to increase, meaning the number of electrons is also going to increase. So more electrons means more energy, which means more chaos. So as you go down each element, it's going to get more crazy, but we'll see that when we're writing it. So now that we know what orbitals are, let's go back to the central question. What are electron configurations? Let's look at this definition again. The electron configuration is the distribution of electrons of an atom or molecule in atomic or molecular orbitals. So basically, the electron configuration tells us which shells electrons are in, which subshells or energy levels they have, and what their orbitals could look like. So let's look at a visual. Here we have nitrogen. Nitrogen has an atomic number of 7, which means it has 7 electrons. Here is a simplified diagram of nitrogen, and we see it has 1, 2 shells. So here's the electron configuration for nitrogen. The electron configuration for nitrogen is read as 1s2, 2s2, 2p3, and as you can tell, there's 3 separate parts. The coefficient to each part means which shell that electron corresponds to, and each exponent of each part means the number of electrons in that part. So 1s2, this means that there's 2 electrons in the S subshell in the first shell. So let's look at the first shell over here. There's 2 electrons, and those 2 electrons, as we can tell, are on the S subshell. Let's look at this, 2s2. This means 2 electrons in the S subshell in the second shell. So we have the second shell over here. We have 2 electrons which are in the S subshell. Now 2p3. This tells us that there's 3 electrons in the P subshell in the second shell. So let's look at the second shell again. There's 3 electrons, 1, 2, 3, that are in the P subshell, and they are in the second shell. Let's look at chlorine now. Chlorine has an atomic number of 17, which means it has 17 electrons. Chlorine has 1, 2, 3 shells, and this is the electron configuration for chlorine. So let's read it. 1s2, 2s2, 2p6, 3s2, 3p5. So chlorine, since it's a larger atom, it's more complicated. But let's go through this. So 1s2. This means 2 chlorine electrons are in the S subshell in the first shell. So those are the 2 electrons there. Then we have 2 electrons in the S subshell in the second shell over here. And we have 6 electrons in the P subshell in the second shell. So P is green. So there are the 6 electrons. And we have 2 electrons in the S subshell in the third shell. So we go to the third shell. There they are. And last we have 5 electrons in the P subshell in the third shell. So there's the 5. And notice how since the exponent equals the number of electrons, when you add the exponents together of this entire electron configuration, you get the atomic number of chlorine. So if you ever get a question on, let's say, which element does this electron configuration correspond to, you can simply add up the exponents and then you get the element. This is a picture of the periodic table, and as you can see, it's split up into sections based on subshells. So over here we have the S block, the D block, the P block, and the F block. It's important to note that each vertical row going down the periodic table is called a group, and each row going across the periodic table is called a period. So when you go down a group, it's numbered. So over here in the S block, we have 1s, 2s, 3s, 4s, and so on. But when you get to the D block, as you can tell, the fourth period, it doesn't start with 4D. It starts with 3D, and it goes to 4D, 5D, 6D. But when you get to the P block, it resumes back to the regular order. So there's no 1P, but there's 2P, 3P, 4P, 5P, 6P. And then we have the 4F and the 5F in the F block. It's also important to remember the number of electrons that each subshell can hold. So for the S subshell, remember, only 2 electrons can exist in each orbital. So for this entire S block, the first 2 elements in this entire period, the ones that belong to the S block, there's only 2 because the S block can only hold 2 electrons. And over here in the D block, remember, D can hold 10 electrons. So this entire portion of that period, it's shaded in green for the D block because 10 electrons can exist in the D block. And for the P block, remember, it's 6 electrons. So in this portion of the period, 6 electrons are shaded red. And I know this sounds confusing, and I'm probably not explaining it well either, but it'll make sense once we start learning how to write the electron configuration. Writing electron configurations. When we write electron configurations, we go from left to right of the periodic table, and we write the configuration for all the elements before the element we're looking at. So, for example, this element that I'm pointing here, it's at 2p. When I write the electron configuration, I don't just write 2p. I write the electron configuration of everything before that too. Let's see how this works. We're going to start with hydrogen. Hydrogen is the first in the periodic table. It has an atomic number of 1, meaning it only has 1 electron. This 1 electron is in the first shell of the S subshell. And there's nothing before that, so the electron configuration would simply be 1s. Now let's look at helium. Helium is number 2 in the periodic table, so it has 2 electrons. Now when we write the electron configuration, remember, we go from left to right, so we have to add everything before that. Hydrogen is the only thing before helium, so we have to take into account that 1s that's already written for hydrogen. So we start with that 1s, and we go across the periodic table to add another electron to that s. So what do you think the electron configuration for helium would be? 1s2, because, remember, 2 electrons in that s subshell. Now let's look at something a little harder. Nitrogen. Nitrogen is number 7 on the periodic table, meaning it has 7 electrons. Remember, we start from the beginning, go from left to right, and add everything in front of that element. So let's start from the first shell. Remember, it's 1s2 since we went all the way across. Then we go down the group. So we have 2s, and remember, s has 2 electrons that need to be filled, so it's 2s2 over here. And then we go across to this p block. And now you see nitrogen is in that p block. So we count 2p1, 2p2, 2p3. And that would be the electron configuration for nitrogen. Now let's try something trickier. Silver. Silver has atomic number 47, so it has 47 electrons. Remember, we go from left to right and add everything in front. So let's start with the first group, 1s. Remember, the s subshell can have 2 electrons in it. So we have 1s2 because we went across it. Now we're going to go down the group, 2s2. And we go across the period, 2p6, because remember, p can have 6 electrons in that subshell. Then we go down the group again, 3s2, and then we go across, 3p6, down again, 4s2. Okay, and now when we go across, we're going to get to the D block. And remember, the D subshell can have 10 electrons in it. So this would be 3d10. And when we go across, 4p6. Now we're going to go down one more time, 5s2. Now this is 4d, the 4d block. And silver is in this block, so now we're going to have to count. 4d1, 4d2, 3, 4, 5, 6, 7, 8, 9. So it would be 4d9. And this is the entire electron configuration. Okay, now that we went over how to write electron configurations, let's try some on our own. So let's try to answer this one. What is the electron configuration of aluminum? Grab your periodic table, pause this video, and try this one. Okay, so hopefully you tried this one on your own, and let's go over it. The electron configuration of aluminum is 1s2, 2s2, 2p6, 3s2, 3p. And the way we got this was, well, first we start from the beginning. We go across, and then we get 1s2. Then we go down the group, 2s2. Across the period, 2p6. Then we go down the group again, 3s2. Across the period where aluminum is, and we have our 3p over here. So hopefully you got this right. If not, it's okay. We'll try another one. So try this one. What is the electron configuration of potassium? Again, pause this video and try this on your own. Okay, so let's go over this question. The electron configuration of potassium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s. So let's start again from the beginning. We have our 1s, go across 1s2. Then we go down the group, 2s2. Across the period, 2p6. Then go down the group again, 3s2. And then we go across, 3p6. And we go down one more time and we have our 4s over here. You might also get a question formatted like this. So in this case, which element is, and then this electron configuration. In order to approach this question, you can either just count up the exponents, because that will lead you to the number of electrons in your answer, and the number of electrons equals the number of protons. So just look at your periodic table, find that atomic number with that number, and then that's going to be your element. Or you could do it the long way and actually do it out. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1, 2, 3, 4, 5. So this element right here, that's going to be your answer, and that's bromine. So bromine would be the element with this electron configuration. So I just want to point that out, that that's a question that you might see. If you understood these 3 questions, great job. That means you learned something. If you didn't, or if you still have some questions, don't worry. That just means you have to practice a little more. But before you know it, you'll be an expert at this topic. Before I end this video, I just want to recap what we learned. So the first thing that we learned was what electron configurations are, and we saw the internet definition for this. So when you think of electron configurations, just think of distribution of electrons, and distribution where? Well, around the nucleus. So remember that picture of the atom that I showed you. So that's not what a real atom looks like. And in reality, the orbitals, that's what's gonna give that atom that crazy look. So what are orbitals? When you think of orbitals, think of where electrons are going to be most likely. So like I said, the orbitals is going to be that pattern, that crazy pattern. And what's going to determine what that orbital looks like? Well, we also learned about subshells. There's 4 subshells, S, P, D, F. And when you think of subshells, think of energy levels. So the higher energy level, F, the crazier the orbitals are going to be. So remember in that diagram, S, there was only one orbital, and the orbital was a simple circle. But the F had 7 orbitals, and it was crazy with the bubbles and everything. So that's what subshells are. And then we kind of briefly went over shells. And when you think of shells, just think of levels, or how far away from the nucleus. So over here we have our first shell, our first level, and then we have our second shell, our second level. And yeah, that's pretty easy to understand. And then in this diagram, we also have our subshells indicated by color here, but like in reality, they're indicated by like how complex the orbitals are. The last thing we learned was how to write electron configurations using the periodic table. That's what we learned last, and that's what the questions tested you on. So hopefully you understood that. And yeah, that concludes the end of this video. Thank you so much for watching. I hope you learned something from this. I had a good time making this video, and good luck to your chemistry studies and future tests. So again, thanks for watching, and see you soon.